Hello. So what we're doing today is two gravity drain tanks, and we're going to be applying a proportional integral controller. So let's see how that um, equation and all that works out. So let's start with what we know. So we have two gravity drain tanks with water or some sort of liquid in them. We're going to have an inlet. It's going to go out of the first tank into the second tank, and then out this one. It's basically the same thing as last time, except we have two tanks rather than three. We're going to do the labeling of our variables and have our different heights. Again, it's the same thing from uh, last time, but a little different. And what we know is constant is our cross-sectional area, and then our drainage hole area. There we go. So we're going to apply what we also knew from our part A equations. So last time we found the change in height with respect to the time, and that equation came out to be 1 over the cross-sectional area multiplied by the inlet flow minus Q1, where Q1 equals the multiplication of our drainage hole and um, the 2 times the gravity constant times the height of the first tank, or whichever one is correspondent to this variable right here. And we do the same for our second tank, which is Q1 minus Q2. So we're going to now define what our inlet flow is going to be, because this is how we're going to find and how we're going to correspond our integral controller. So I'm going to say our initial flow rate or initial inlet flow rate plus the KC, which if you remember when we did the coding, KC is the proportional controller parameter. That's how we changed what the plot looked like and how we got rid of the oscillation and flattened it out, times the error, where the error is the set point minus the uh, height of the second tank. And this is actually called proportional offset. And this is only due to the fact that we have only proportional controller. We don't really have an integral controller to balance that out. And that's one of the reasons why we didn't reach our set point in part A. It's because we didn't have an integral controller to eliminate this offset. So we're going to be applying that today. So we're going to have Ki, which is the parameter we're going to use for our integral controller. And then since it's an integral controller, we need an integral. So we're going to do 0 to t, and then on the inside is just what our error is. So HSP minus our height of tank 2. And we're going to take the derivative of our tau, which this will represent the time axis. So this is the time and this is the complete time axis. So I guess in a sense you have like, this is t, but then our time axis as a whole is what tau is representing. And how we're going to be solving this section, because it's a little bit it's a bit mucky, so we need to solve this so we can actually utilize it in our code. So we're going to be using the fundamental theorem of calculus. I'll label it as FTC. And what we're basically saying is we're going to take E int, which is the integral, and we're going to label that as HSP to d tau. And we're going to take the derivative of that. So, and that if we take the derivative, this basically just cancels out the integral, because we're taking the derivative of the integral. And according to the fundamental theorem of calculus, this is what it will do. So we're left with whatever our error is, which is the set point minus tank of height 2, or the height of tank 2, my bad. And we're just going to plug this in. So we're left with our Qin initial plus the Kc times error plus the Ki times the integral. And then we're just going to plug this into our previous equations, specifically dh1 over dt. So have our Q in initial, not Q in, plus the Kc times our error plus the integral parameter En, and then minus Q1. We're also going to write it for our second one. So 1 over A, Q1 minus Q2. And again, Q1 and Q2 is essentially just the AH times 2GH, or whatever its and the H is going to be whatever it's corresponding to this variable. So this is going to be H2 right over here. And we're going to be using these equations in our collab. So we'll see you at that stage. Okay, so this is the coding. We got our collab all started up. I already wrote all the imports and everything that we need for this code. So let's just get started. Gotta turn the keyboard on. 9.8, and this is just our gravitational constant, of course. And then we already know our cross-sectional area, which is 1, and that is meters squared. We also know our drainage hole area, which is 0.1, and that's also meters squared. And then what am I missing? Oh, that's right, our Q initial, which, as in the problem statement, it's as 1, which is meters cubed per second. And then we also want to define what our H naught is, and we found this from doing a derivation in part A. So we found this to be Q initial divided by AH. We will square that, and this will be divided by 2 times G. And then we can find our set point after that, which is 1.2, just 20% higher than our initial steady state, which is what part A had us solve for. So we're just going to use that same principle here, and that is multiplied by the H naught value. And then we're also going to set our controller parameters, which Kc we found as 0.6 last time, so that's what I'm going to be using here. We'll just call this controller gain. And then we have our new parameter, which is for the integral controller, and put that as 0.1, and label this as our integral controller gain. And also label our t end, which is 1000. It's essentially just saying how long the simulation is going to last. And then we have to define our t plot, which is np dot line space tn, and then 1000 is just saying for the 1000 seconds it's running, it's going to have 1000 evenly spaced plots. And then we're just going to find out what our two values are looking like. So 5.1 is our initial height that we're given, and then 6.12 is our set point. This is what we're trying to reach. So, excuse me, let's get started. We're going to define our right-hand side, and it's just going to be our time and then vector, and our vector is just our heights and our e integral or error integral value, and this is just going to allow us to see the changing heights and error value. So that's what the vector does basically. And we have our Q1, Q2, which is our outlet flows, and we're just going to define that as, yeah, that's correct. And then 2 times G times H1, and then Colab helped us a little bit there just to fill it out. And this is just what we found before, so it's this right here, except in code. And then we're going to define what our error is. Sorry. And then we're going to also show what our initial flow rate is, which is what we found in the problem previously. So that is our initial plus Kc times our error. And then, if you remember, we had our Ki. We're going to multiply that by our eint. And this is just going to return our normal equations, which were Qin minus Q1 divided by the cross-sectional area. And then we can just go ahead and copy to paste this. Change this to Q1, change this to Q2. And then we also want to find what our error is. Shift enter to make sure we didn't do anything wrong. And then almost done with the home stretch. We're going to do our solve IVP, and this is just going to allow us to solve the equations and display it. So have that, and then we need, forgot if this is supposed to be brackets or parentheses, but screw it, we'll just try it out. H naught, and then 0, and then our method will be redow, and then we'll have our dense output as true. Oh, and it works, so we were correct. And we will set our H1 plot, H2 plot, and our error integral as res.sol t plot, and this will just help us plot it out essentially. And we need a way to actually see the plot, so that's how we're going to make our fig equals make underscore subplots. Yep. And then fig dot add underscore scatter. This is how we're going to define what our plot will look like essentially. So this is, I think X is our t plot, which is time, and then our Y should be our H1 plot, and then our mode will be using lines, and then our name will be H1, and we'll use Colab to just fill this out, which is the same thing. And then we're also going to need to update the layout. A good plot means good pay, hopefully. And our width, which I found is better as 800. And then our height, which is better as 400. And then our template that we'll be using is plotly underscore dark. Everything checks out. Try it out. There we go. Oh wow, okay. So we did reach the 6.12 as these random values, but yep, there we go. So I'm just gonna keep in mind that our ki with 0.6 and 0.1, we did manage to reach that 6.12 set point and less oscillation. But let's see what happens if we change it to like 0.05. And look at that, it's still at that 6.12, yet we're decreasing our oscillation at the start. So if we move that down a little bit more, it seems like it is reducing the amount of oscillations at the start, which is a good thing because it's not it's reaching our steady state eventually, but it's still oscillating quite a bit. And then yeah, so it looks like we found what the Ki and the Kc value contribute to in terms of plots. So yeah, thank you.